In this video, we want to continue looking at probabilities. The first probability that we want to look at is what we call a compound event. So a compound event is when more than one event is combined together. It could be two events, three events, or four events. So the probability of A or B happening is equal to the probability that A occurs, or B occurs, or they both occur. So think about students that are taking math, or they're taking science, or maybe they're taking both. So all three groups of those students would be counted in a compound event. A contingency table is one in which we use it to show the distribution of one variable in rows and another in columns. Now these are variables of the same individual happening. Let's look at this particular contingency table. So the following data represent the number of speeding tickets issued to individuals in the past year and the gender of the individuals. So what this 97 means is that there are 97 females with 0 tickets. There are 14 females with 1 ticket, 3 females with 2 tickets, 1 female with 3 tickets. Then we go to the males. On any contingency table, if you do not already have numbers that are considered totals, you need to total up each row and each column and then find the grand total. The grand total tells me exactly how many individuals have been asked the question or researched. So in this particular case, females, we have 97, 14, 3, and 1 for a total of 115 females. We have 71, 7, 1, 3 males for a total of 82 males. Now let's total up each column. We have 97 and 71, so we have 168 people with 0 tickets. 14 and 7, we have 21 individuals with 1 ticket. 3 and 1 is 4 individuals with 2 tickets. 3 and 1 is 4 individuals with 3 tickets. When we add up the 115 females to the 82 males, we get 197 individuals. The same should be true if we add the 168, 21, 4, and 4. We should also get the 197. This indicates that there were a total of 197 individuals surveyed for this particular table. So using this information, we want to determine the probability a randomly selected driver is female. So if we're looking at females, that is all of these. So the probability of female is equal to a total of 115 out of the total number of individuals that were surveyed, 197. We divide this out and we get 0.584. So the probability a randomly selected driver is female is 0.584. Now let's look at the next one. Determine the probability a randomly selected driver has been issued 1 ticket in the past year. So let's look at our table. 1 ticket is right here. There are a total of 21 individuals with 1 ticket. So the probability of having 1 ticket is equal to those 21 individuals out of the total 197 individuals. Divide this out and we get 0.107. So the probability a randomly selected driver has been issued one ticket in the past year is 0.107. Determine the probability a randomly selected driver is female and has been issued one ticket in the past year. So let's go back up to our table. And so we're looking at female right here. And we're looking at one ticket right here. What this shows me is where I'm looking at a contingency table, their intersection is the and portion. So there are 14 females that have been issued one ticket in the past year. So whenever I'd go to do this, I'm wanting to look at the probability of female and one ticket. Now remember that these are two characteristics of one individual when we're talking about contingency tables. So there are 14 females out of 197 people that were surveyed. There are 0.071. So the probability that a randomly selected driver is female and has been issued one ticket in the past year is 0.071. Probability a randomly selected driver is female and has been issued one ticket in the past year is 0.071, or 71 thousandths when we're talking about this. Let's look at another example. The table below represents the college degrees awarded in a recent academic year by gender. So we have bachelor's, master's, and doctorate. Now, the first thing that I need to do is I need to find a total number of males and a total number of females. So if I add these up, I have 808,801 male. I have 1,098,371 females. I need to do the same thing for each individual degree. So I have 1,348,503 bachelor's degrees, 512,645 master's degrees, and 46,024 doctorate degrees. If I add these two numbers up, the male and the females, and then I add up all of these, I get a total of 1,907,172 individuals. Recall that this is our very first step when we're looking at contingency tables. So let's look at our first example. Choose a degree at random, find the probability that it is a bachelor's degree. So a bachelor's degree, we're looking here. We're just looking at one characteristic. So the probability that a person has a bachelor's degree is equal to the total number of bachelor's degrees, which is 1,348,503, out of the total number of people that were surveyed, which is 1,907,172 individuals. I do this division, and I get 0.707, or 707 thousandths would be the probability. So the probability a degree chosen at random is a bachelor's degree is 0.707, or 707 thousandths. Now let's look at the next one. And here we want to look at a doctorate degree or a degree awarded to a woman. So we're looking at the doctorate degrees or those awarded to a woman, a female. So when we look at things that have an or, These are two characteristics of the same item. So I'm going to look at the probability of a doctorate degree or a woman. This is going to be equal to the probability of a doctorate degree plus the probability that it's a woman. And notice that I have a little bit of overlap here. These 21,000 people have been included in the doctorate, but they have also been included in the female. I don't need to count them twice, so what I'm going to do is I'm going to subtract out their overlap. The degree is a doctorate and a woman. Again, it's because these 21,000 have been included in this blue circle and in this yellow circle. We don't need to include them twice. So, those that have a doctorate degree is 46,024 out of the 1,907,172, plus the total number of women, which is 1,098,371 out of my 1,907,172. But again, these 21,000 right here have already been counted in the doctorate and in the female, so I need to subtract those out. So I'm going to subtract out 21,683 out of my 1,907,172 people. When doing this, notice my denominators are all the same, so I can just look at the numerators. I can add and subtract my numerators for a total of 1,122,712 on my numerators out of the 1,907,172, and I'm going to get that that's 0.589. The probability a degree chosen at random is a doctorate degree or a degree awarded to a woman is 0.589. Again, we are subtracting out that overlap because these 21,000 individuals were counted with the doctorate and with the woman, so we can't count them twice. A doctorate degree awarded to a woman. So this is where we're looking at them happening together. So let's go back up to our table. I'm going to get rid of some of these things. Now I'm looking at a doctorate degree awarded to a woman. So here's a doctorate degree awarded to a woman. So it's strictly this number, the 21,683. The probability of a doctorate and woman is equal to 21,683. That's the intersection over the 1,907,172. Divide this out, and I get 0.011, or 11 thousandths. The probability a randomly selected degree is a doctorate degree awarded to a woman is the 0.011, or 11 thousandths. So now we want something not a master's degree. So if I come back up here, and we want it to where it is not a master's degree. So that means we don't want these. We want bachelor's and we want doctorate. So we can add these two. Now notice that bachelor's and doctorate do not overlap. There's none of these that are counted here. So whenever I come down here and I look at probability that it's not a master's, that's equivalent to the probability of a bachelor's plus the probability that it's a doctorate. You'll notice that I do not do any subtraction because there's no overlap. There's no item that can occur the same time. So I end up with the bachelor's degrees. There was 1,348,503 out of my total 1,907,172, plus the number of doctorate degrees, which was 46,024 out of 1,907,172. Again, my denominators are going to be the same, so I'm going to add my numerators, and I will get 1,394,527 out of my 1,907,172. I do this division, and I get 0.731, or 731 thousandths. So the probability a degree selected at random is not a master's degree is 731 thousandths, 0.731. I'd like for you to practice some of these. In the next video, we will look at the actual rules and how to write those out. Let me know if you have any questions.